For some of you, the book that I'm holding may invoke some feelings of nostalgia, but for others, maybe some feelings of inadequacy. These are Magic Eye stereograms. They created a sensation when they came out in the 90s, and it's easy to see why. A 2D picture that creates a 3D image if you do a certain thing with your eyeballs?
Look, there's a spaceship! That is so cool!
Where is it?
I feel like I didn't realize back then how neat these are, but I do now, so let's talk about it. Stereograms can be designed to be viewed cross-eyed, but all the ones in this video are for divergent viewing. That means that rather than having your eyes pointed at the image itself, you're supposed to over-diverge your eyes, as if you're looking through the image at something beyond it. It's tricky because normally the lens in our eyes focuses on the thing our eyes are pointed at. But for these, you need to focus on the image while pointing your eyes at a spot beyond it. Some stereogram books come with a handy guide. These 2 dots at the top should help position your eyes. You want to relax your eyes until you see double vision, so 4 dots, but then pull it back so that they overlap and you get 3 dots. Then glance down and you should see the Cathedral of St. Basil in Moscow. If you still can't see them, there's a trick you can do in Photoshop. Duplicate the image and use the difference blending mode, which highlights where the 2 images are the same in black. Then if you pull the top copy across, a silhouette of the hidden image appears. I'll explain how all of this works, but first it helps to understand how Magic Eye emerged from a long history of research on visual perception. So our pupils are about 60 millimeters apart. That means each eye gets a slightly different picture projected onto its retina.
Camera 1, camera 2, camera 1, camera 2.
The reason we don't have constant double vision from these 2 different pictures is that the brain immediately combines them into one. And in doing so, it uses the differences in the 2 pictures to add depth to our visual perception. This is stereopsis, or 3D vision, and it was first described by an English inventor in the 1830s, Charles Wheatstone. It took scientists a while to realize that having 2 eyes gives us depth information, because it's not the only depth cue that we have. Shut one eye, and it's probably tough to thread a needle, but the world doesn't become completely flat. Wheatstone revealed stereopsis with a device that could display a slightly different image to each eye, simulating how each eye would take in a real-life 3D object, but with flat images. And it successfully tricked the brain into perceiving depth. This was the first stereoscope. After the invention of photography, a Scottish physicist named David Brewster developed a handheld stereoscope, and a version of it was displayed at the Great Exhibition in London in 1851. Queen Victoria was reportedly delighted by it, and before long it was a super common household item throughout the last half of the 19th century. The dual photos were made with stereo cameras, which have 2 lenses spaced eye distance apart, and they were used to document all sorts of historical events. Stereo cameras eventually went out of style, but you might recognize this more recent version of a stereoscope. And that same principle of creating a 3D image by showing each eye a slightly different picture continues with 3D glasses and virtual reality headsets. But it's not all for amusement. Stereoscopy has also been used for all sorts of aerial imaging applications. British photo interpreters in World War II used overlapping images taken from airplanes to detect Nazi military assets. This ability of stereoscopes to thwart camouflage by making objects pop out of seemingly flat aerial images inspired the development of the random dot stereogram. That's the kind with the hidden 3D image. In 1960, a leading vision researcher named Bela Ulez created a computer-generated random dot stereogram. He started with a grid of random dots and duplicated it, but in the copy, he shifted a square patch of the dots slightly to the left, filling in the leftover space with other random dots. If you looked at these images through a stereoscope, or if you've trained your eyes enough to free-fuse the images by pointing one eye at each one, you'll see the square pop out from the random dots. With this experiment, Ulez showed that the brain could detect depth even without any recognizable objects in the images. What's different about the Magic Eye type of pictures, also known as autostereograms, is that you don't need to have any special device to view them because it's one image instead of 2. Instead of 2 different pictures, autostereograms repeat the images within one picture. To understand how these work, let's first look at a simpler type of autostereogram. This is a so-called wallpaper stereogram. It doesn't have a hidden image. Instead, it just has repeating patterns that appear at different levels of depth when you diverge your eyes. So relax your eyes as though you're looking through the screen, and you should see the airplanes fall back with the rest of the grid. The dinosaurs, which are repeated at slightly closer intervals, should appear in a plane that's nearer to you. And the cakes, repeated at even shorter intervals, should be even nearer. You should also see one more of each icon than there really is. There are only 6 cakes in the image, but you're seeing 7. And all of the icons should appear to be slightly bigger than they really are. So why is this happening? This diagram shows the view from above your head, and these dots represent icons on a simple autostereogram like the one I just showed you. When you let your eyes diverge, instead of fixing them on one of the icons, each eye is seeing its own icon. Because your brain is used to turning 2 similar pictures into one, it assumes the 2 icons are actually one icon that's further back and larger, rather than 2 that are closer. This illusion happens across the image, with every pair of repeated icons being wrongly interpreted as one. The rightmost and leftmost icons don't have pairs on their other side, so you end up with 7, 5 illusory icons plus the edge ones. Pairs that are repeated at closer intervals, like the cakes were in the previous image, appear nearer to you. So it's the interval of repetition that can be manipulated to adjust depth. And if we go from icons to something smaller, you can start to see how they build a 3D image that can be easily camouflaged with noise. You can see that in this stereogram we made using letters instead of icons. If you diverge your eyes, you should see some of these words pop out to reveal a message. The 2 asterisks are there as a guide. You should see 3 of them, and then slowly bring your eyes down. What's happening is that the regular repetition interval in this image is 16 characters, including spaces. But in this interval, we removed a letter, bringing this pair slightly closer together than all the other pairs. So as your brain fuses that pair, the resulting image appears closer to you than the rest. Autostereograms start with a base pattern that repeats across the image, but with select dots or pixels shifted to vary the depth and compose the 3D figure. The first random dot autostereograms were made by hand in the 1970s. This one by a Japanese graphic designer shows an array of hidden squares. And this one, by a Swiss painter, has overlapping rectangles. But by the 1980s, vision researcher Christopher Tyler and programmer Maureen Clark had come up with an algorithm that could embed more complicated depth images into a random dot autostereogram. Using the red dots as a guide, you should see a 3D surface pop out that's much more complicated than a wallpaper or a simple rectangle. The algorithms that produce these images work from a depth map. That's a black and white image that tells the program to make the repetition interval shorter for the dots that make up the lighter and nearer parts of the image. In the final product, you can't tell which dots have been shifted or how much, but if you go back to that Photoshop trick and scan through the image, you can see how the nearest parts of the shark repeat at closer intervals than the most distant parts of the shark. Everything in the base image repeats at the same interval, except the dots that make up the shark. In the 90s, artist Sherry Smith and engineer Tom Bechet developed their own method, using bright, colorful patterns as their base. They branded them as Magic Eye, and published the first of many books in 1993. After that, they were everywhere.
Hey, can you see it? You gotta see it. You really gotta see it. Come on, give it a try.
Magic Eye put out VHS tapes that included animated stereograms, they sold posters, they were printed in newspapers, and some people got left behind.
I've been staring at this thing for a week now, from opening till closing, and I can't see a goddamn thing!
If you still can't see them, it may be that you have some visual impairment that affects your stereo vision. But for most of us, learning to diverge your eyes just takes a little bit of practice.
Today's my day. I brought a lunch and a soda, and I'm not gonna leave until I see the sailboat everyone keeps talking about.